Hey guys, in this video I'm gonna show you the concepts of limit and its connection to continuity and convergence. So basically we're gonna talk about three concepts: limit and continuity and convergence. Okay, so when we talk about limit to continuity, we basically put the setting on the functions, right? And for limit to convergence, we put setting we put a setting on the sequence of real numbers. Okay, so now let's get started. So first of all, let's define what is a limit, or how are we gonna call the limit of a function. Okay, so now let's let x and y be two metric spaces, and this is just the natural way that we define the function, right? Okay, and now E is contained in X is the domain of the function. So F maps E into Y, and we are going to look for the limit of function at the point P. So now P is the limit point of V. Okay, P is the limit point of V, and we say that Q is the limit of F as X approaches P if it satisfies such condition, which is for every epsilon less than 0, there is a delta such that the distance between X and P is smaller than delta. Okay, now the X is what? X is the point that approaches getting closer and closer to P, but X is not equal to P, right? And on such condition, when when the distance between X and P is smaller than delta, we have the distance between Fx and Q is smaller than epsilon. Then we say Q is the limit of the function. So if we set it on this graph, okay. Suppose we are looking for the limit of the function at the point P. So P is here, and well, in this case we know that Fp is actually, in this case Fp is Q, right? But when we are looking for the limit of functions at such point, x is getting closer and closer to P, but x is not equal to P, right? So when we're looking for its limit, we don't actually care about what exactly the value of this function at that point, right? Okay, so whatever epsilon that you are choosing, suppose we have epsilon like this. So here's epsilon plus fp. Okay, actually we can't see fp. So you are trying to show that q is the limit of function at point P. So here's actually epsilon plus P and epsilon minus P, right? Okay, and okay, now you are choosing such interval, right? And for this interval, you can find such data, right? Because, well, for epsilon plus P, you may find this interval and this one. Okay, so now you find the interval P minus delta to P plus delta, right? Such that the condition is satisfied, right? Although in the definition it seems that we are firstly choose delta, because we say that the distance between x and p is smaller than delta, implies the distance between fx and q is smaller than epsilon, right? But actually, since we are saying that for every epsilon we can find a delta, so actually delta is dependent on epsilon, right? If we say the relationship between delta and epsilon is certain kind of function or a mapping, right? So the actually delta is dependent on epsilon. So it's like you first fix epsilon, then when that whatever epsilon you are choosing, you can always find the delta. It's pretty much like the limit point that we talked about previously, right? Okay. Well, still we see this. We look at this graph. Just now we define. We fix epsilon this way, but if you like fix, you wanna choose epsilon smaller and smaller, it's totally fine because whatever epsilon you're choosing, you can always find such data, right? And since we are looking for the limit, we kind of like, we wanted to choose epsilon extremely small, right? We wanted it to be so small, but however small it is, you can always find delta, right? You can always find delta such that the value of functions at that small interval is very close to Q, the limit that you are trying to prove, right? So this is a definition of limit, and the reason that we want to study limit, I think, actually is that we want to like study a very important character of function, which is continuity, because actually a function, if it is continuity, it actually give the function a lot of like good properties, or some properties that somehow like correspond to our instincts, something like that, because the functions that we've met a lot are those those good functions, those with like good properties. And actually there are a lot more functions that's kind of like pretty bad functions. But so how are we gonna like discriminate good and bad functions, right? And continuity is such a good way to kind of like separate, well, good or bad functions. Okay, so what is continuity? Continuity, or in other words, I mean, something that's not terminology in mathematics is something pretty similar or pretty close to smoothness. And well, smoothness is okay. Actually, smoothness requires more than continuity. Sometimes it requires also like a differentiability or something, but continuity is a requirement for a smooth function. And smooth, as I said, it's not a terminology in mathematics, so it's kind of like help you to understand why we want to study continuity of function. So the definition of continuity, still we let x and y metric spaces and is containing x, and now I have to take care of this. So P is a limit point of V. Okay, here actually we have two cases. First, P is a limit point of E, and the second case is P is not a limit point of V, right? So in the first case, if P is a limit point of V, and now still F maps A to Y. So in which case we call F is continuous at P. Okay, if for every epsilon larger than 0, there exists delta larger than 0, such that the distance between x and p smaller than delta implies the distance between fx and fp is less than epsilon for all x that is contained in E. So that is to say, well, first of all, the function has to have a limit at p, right? Well, the definition here is the same as that we define the limit, right? Limit. Okay, and the different, a little bit different is that here we are saying that the limit is actually, here we say the limit q is a limit of a function, but in this case, if it's continuous, then the limit must be the value of the function at that point. Okay, fp, the value of the function at that point, right? So to say to kind of like define the continuity, for the limit we don't actually care about whether the value of the function at the point, right? We just care about those points closer to p, right? The value of the value of functions at the points closer to p. But for a continuous function, we need to focus on not only those closer to p, but also the value of the function at p, and fp must be the limit of that function. Okay, here's the difference. And by the definition that we talked just now, it only implies that fx is continuous at a point p. So if f is continuous at every point of E, then we say that f is actually continuous on E. So sometimes we say some functions is a continuous function. That is to say, the function is continuous at every point of E of its domain. Okay, and this is the first case. The second case is when P is not included in the limit points of E. Instead of a limit point of E, then f is continuous at P by definition. So this is actually a simpler case because you don't need to worry about the distance of something. If P is not a limit point, then you directly say that f is continuous at that point. Okay. So next part is I wanna introduce limit and convergence. So now we transfer the setting on a function to the setting on a sequence of real numbers. Suppose now we have a sequence of real numbers an. So how are we going to define the limit of a sequence? We say that R is the limit of an if the language of the language of defining a limit is pretty much the same, right? For every epsilon larger than 0, there exists k. Okay, now here's the difference. There exists k, but it's pretty reasonable, right? Because now if you say a sequence, like say a sequence as a function, then the domain is now discrete, right? Its domain is simply the positive integers, right? So in the previous case, we say there exists a delta larger than 0 such a distance between x and p smaller than delta. In this case, we say there exists k, and k is a positive integer, right? Such that when n is larger than k or larger or equal to k, an minus l, the distance between an and l is smaller than epsilon. So it's like the limit of a sequence to looking for a limit of a sequence. We don't care those in the front, right? We only care those after k, those terms after k, right? So it's like, well, suppose we say the limit of the, okay, suppose this is R, and here is the sequence of real numbers. We say the limit of the sequence is R. Then whatever epsilon you are choosing, like here I choose this one, this epsilon, r minus epsilon, r plus epsilon. Okay. Then you can always find the k. Well, in this case here, when n is larger, case here, when n is larger than k, all the points, all the terms of an after ak is in this small set, right? So so looking for the limit of a sequence is kind of like you are looking for those at the end of the sequence. But actually, at the end of I don't think it's correct to say at the end of the sequence, because sequence can be infinitely many. But so it's like, but even it's infinitely many, those in the front, those from the first term to the case term are finite, right? So after the case term, all the terms of the sequence, the value of the sequence is getting closer and closer to L, right? And whatever however small the interval you are choosing, you can always find such k. Okay, this is the definition of limit under the sequence setting. I think it's pretty much simple and straightforward. Especially when you are looking, with the help of the graph. Okay. So for the convergence, if an has a limit, then we say that an is convergent. So actually, when I studied this definition of convergent, I was quite puzzled by these two definitions. I feel like they are pretty much the same. Well, since an has a limit, then we say an is convergent. Well, then why we bother to have another concept like convergent? Why we just say that an has a limit, then it has a limit, right? We can use a lot of for those properties relative to convergent. We can simply use a limit instead of convergence, right? But well, I don't actually say the formal or very rigorous explanation of why people use convergence and limit at the same time, but I feel like when you study more about convergence, some properties like that, well, convergence is using the concept of convergence is somehow much more convenient than constantly saying that a function has a limit. Maybe it just saves time and it's more efficient, right? Okay. Other than convergent, we have divergent. So we say an is divergent if for any m larger than 0 there exists k. And also case in positive integers, such that when for any n larger than k, we will the value of an will be larger than m. So it's like the an is so whatever m you are choosing, the function function. There must be some terms in that sequence that are larger than m, and sometimes that I say is those after the case terms. So still we can see it from a graph. So this is okay. So say we are choosing m here. Then, well, k can be for every m you can choose a k. For the fixed m that I choose in this case, I can find a k, right? So in the function setting, we say delta is something that dependent on epsilon, right? And in this case, k is something that depend on m, right? Because when you choose m, then you can choose a corresponding k, such that the terms after k are all larger than 0, right? And in the previous case, the same. K is dependent on epsilon. Okay. And another thing to mention is that if a sequence can be neither convergent nor divergent, it can oscillate. That is to say, it's not the terms, the values of the sequence is not getting closer or closer and close, is not getting closer and closer to some number, and it's not like diverge. It's not divergent. It's not like you can however large the number you choose, all the rest of the terms in that sequence can be larger than the number that you choose. No, it's not that case. It's like, well, say an is -1 to the nth power. Then it's like jumping from -1 and 1, right? So it's not getting closer and closer to any point. And if you choose like m equals to 2, you can't find such case, such that the function, the terms of functions are all larger than 2, right? So it's neither diverge or converge, and it oscillates. Okay, this is concepts about limit to convergence. So this is basically I want to introduce in this video. It's quite simple and straightforward. It's mainly about 3 concepts, but these concepts are pretty like critical to the properties and propositions in the like functions, continuous functions, and convergence of a sequence. So maybe next video I'll introduce some properties of functions, continuous functions. Okay, hope you have fun, and bye bye.